Hello everybody, my name is Erik Meinicke-Schmidt. I'm Dean of the Faculty of Science at Aarhus University in Denmark. It's a great pleasure to welcome you to our university. We are proud that NASA has asked us to host this worldwide press conference on the results of the Kepler mission dealing with stars. And now, without further ado, I will pass the word to Professor Natalie Battaglia, who is a Deputy Science Team Leader at NASA. Natalie, please.
Thank you so much. Kepler mission and a professor of astronomy at San Jose State University. I'd like to welcome you to this media webcast where we will discuss a series of results from Kepler's Astro-Seismic Science Consortium. Results that highlight the impact that Kepler is having on stellar astrophysics. You can find this briefing, link to the webcast and other related materials by going to www.nasa.gov/Kepler. I'd like to start by describing Kepler's primary objective from a NASA standpoint. So if I can have the first slide, please. Kepler is a space-based telescope, as you can see in this slide, orbiting the sun, and it's using transit photometry to detect planets orbiting other stars in our galaxy. And by transit photometry, what I mean is, Kepler is measuring the brightnesses of stars very, very precisely, with the objective of detecting very slight periodic dimmings of light that would occur if you have a planetary system that's aligned so that as the planet orbits, it passes directly between the disk of the star and the Kepler Space Telescope, thereby blocking out some of the light from that parent star. And Kepler has the sensitivity to detect a dimming of light from a planet as small as an Earth orbiting a star like our sun. And so its objective is to learn if Earth-like, Earth-sized planets in our galaxy are abundant. But actually, we're not here at all to talk about planets today. We're here to talk about stars. We're here to share this series of new results on stars in our own Milky Way galaxy. And these results come from this partnership between Kepler and our international partners that comprise the Astro-Seismic Science Consortium. This is a group of more than 400 astronomers around the world that are using Kepler data to study the stars themselves. Now, it was recognized years before the Kepler spacecraft was even constructed that if we had the sensitivity to detect an Earth-sized planet, we also had the capability of transforming our knowledge of the stars themselves. And the Kepler KASC, Kepler Astroseismology Science Consortium partnership was born out of that realization. Now, no dollars are actually exchanged between different nations in this process. On the one hand, you have the US, who's providing this instrument and technology and this software pipeline that analyzes the data. And on the other hand, you have the international partners that are providing human resources, ingenuity, and scientific expertise to analyze this data and tell us something about the stars. So we're not just getting a great legacy of science results, although that's certainly true about stars. There's more to this story. The results from the Astro-Seismic Consortium are of great interest to Kepler team members for the following reason. Our knowledge of the planets that Kepler discovers is only as good as our knowledge of the stars that they orbit. And the Astro-Seismic Consortium has the potential for some of the stars we are observing to deduce the fundamental properties of those stars, as you'll hear by one of our panelists in just a second. And so I think that this is a very valuable symbiosis and a very valuable partnership that we've created here. Back in January, our NASA administrator, Charlie Bolden, gave a keynote address at the American Astronomical Society meeting in Washington, D.C. And speaking of the future of space-based missions, he said the following: "One facet will be common to all. We must develop a stronger partnership with the international community. The cost and complexity of space programs require that both the achievements and that cost be shared among many nations, for no one nation can carry this burden alone. And these words really rang true to me as I sat there in the audience, and I see Kepler as this shining example of exactly that kind of a partnership, in which all of the potential and possibilities that Kepler has will be fully realized. And so with that, I'd like to introduce my Danish colleague here, Hans Kelson, from Aarhus University. Hans is the project scientist for the Kepler Astroseismic Science Consortium.
Thank you. So, exploring distant stars has taken on a new life thanks to the wealth of data that we get from NASA's Kepler spacecraft. The large number of researchers which are organized in this Kepler Astroseismic Science Consortium have characterized hundreds of stars observed by Kepler. And we use their natural pulse in their light variation to study new parts or get new insights into the structure and evolution of stars. The variation in brightness for a star are caused by oscillations within the star. So the oscillations that we observe reveal information about the internal structure of the star in a similar way as seismologists use earthquakes to study the core of the Earth. So what we do is seismology on stars, a discipline that we call astroseismology. This first illustration shows two examples of stellar oscillations. What we measure with Kepler is the period of the oscillations. And since the period of the oscillations depend on the properties of stellar matter and the structure of a given star, we can use the oscillation periods to study the core of stars. In a way, we use this to touch the stars. And the Kepler data provides us with the most accurate measurements on stars that we have ever made. In this next slide, I show the Kepler light variation for 3 stars. And we will now present the fascinating results of analyzing those light curves or those light variations. And to do this, we have 4 Kepler scientists that will serve as the panel today, and I will start introducing those 4 panel members. 3 of those people are in fact calling in via telephone, and the first of those will be Travis Metcalf from the National Center for Atmospheric Research in Boulder in Colorado. He will present the results for this star called KIC 11026764. And then we will have 2 members of the Kepler team presenting results for the red giant stars. This is the star you see in the middle. And those 2 members are Daniel Huber from University of Sydney in Australia and Thomas Kallinger, Universities of British Columbia in Canada and Institute of Astronomy in Vienna in Austria. And those 3 people will be connected via telephone. And here in Aarhus we have also Katrin Kohlenberg from Institute of Astronomy in Vienna in Austria, and she will discuss the results of analyzing RLeros. So then I will pass the word on to Travis Metcalf.
Thanks very much, Hans. I'd like to start by saying a few words about what motivates us to learn about distant stars when our own star, the Sun, is so much closer and easier to study. One motivation is to learn about the past and future of our own Sun by studying stars that are younger or older, something that we obviously can't learn by studying the Sun by itself. Another motivation is to determine whether the Sun's a typical star or if it's peculiar in some ways. We need to study stars that are larger and smaller than the Sun to make sure that we understand stars in general and not just the possibly strange one next door. The main result of our study of the Kepler target KIC 11026764 was to measure the size and age of this star more precisely than for any single star other than the Sun. I'd like to explain how these measurements are possible with astroseismology and why they're important for Kepler's exoplanet mission. So if I could have the next slide. So doing seismology of stars is a bit like taking an ultrasound image, but the stars generate their own sound waves from the boiling motions near the surface. The tone of these sound waves is so low that even a whale would have a hard time hearing them. The sound waves travel down into the star and bring information back to the surface where Kepler can see as tiny flickering in the brightness of the star. Now, this flickering is not random, but it has an underlying order, like the notes of a musical instrument. To measure the size of a star, we essentially measure the tone of these musical notes from the starlight. Just as it's easy to hear the difference between a note played on a cello and a violin, larger stars naturally flicker in lower tones, while smaller stars flicker in higher tones. This particular Kepler target measured in at slightly more than twice the size of the Sun. So the next slide, please. Stars are powered by nuclear fusion, which converts hydrogen into helium in energy. As stars grow older, the helium slowly builds up in their cores. Now, some of the waves from the surface travel straight through the center of the star where fusion is happening. This is like the white line in the top diagram on the slide. Others turn around and go back to the surface before they reach the core. This is like the colored lines in the diagram. So to measure the age of a star, we compare the properties of the waves that travel straight through the center with the waves that don't to determine how much hydrogen has already been converted into helium. Because helium is more dense than hydrogen, sound waves travel through it more quickly, which changes the tone of the notes that we measure at the surface. Now, this Kepler target is about 30% older than the Sun, and it has hydrogen burning in a thin shell surrounding the helium core. So why does the Kepler mission care about measuring the sizes and ages of stars? Well, the method that Kepler uses to discover exoplanets, the so-called transit method that you heard about earlier, only reveals the size of the planet relative to the size of the star. So by measuring the size of the star, we can determine the absolute size of the planet. And because planets form at the same time as their host star, when we measure the age of the star, we also know the age of the planet. So this allows us to study how stars and their planetary systems change over time. Now, no planets are currently known around this particular Kepler target, but the techniques I've described can also be applied to the stars that do have planets. So with that, I'd like to hand it over to Daniel Huber.
Thanks a lot, Travis. So the next two presentations, we're going to be talking about another class of pulsating stars, which astronomers refer to as red giant stars. Red giants constitute the future of our Sun, which in about 5 billion years from now will expand to many times the size that it is now. Now, this process is not instantaneous, but takes stars through several stages of their evolution in which they gradually expand, so the radii get larger, and they cool down, which gives them the reddish color. Thanks to the unprecedented quality of the Kepler data, we have now discovered that literally all red giants, no matter which size or evolutionary stage, in a sample of over 1,000 stars observed with Kepler, they all show stellar oscillations. Now in the slide you see, this illustrates basically the wide range of stars of red giants in which we have detected these oscillations. You can see the size of the Sun compared to the smallest Kepler red giant, where we have detected oscillations, which is only a few times bigger than the Sun, and the largest Kepler red giant, where we detected oscillations, which is many dozen times bigger than the Sun. Now, this is the widest range of evolutionary stages and sizes for which we have detected these oscillations with a single instrument, and will allow us to study the future life of our Sun in a much greater detail than ever before. Can I have the next slide, please? In the next slide, you see a graph of actual Kepler data. It shows you time versus intensity for 4 different stars, each in a different color. Now, I just mentioned that the Kepler data shows that all red giants oscillate, but not only do they oscillate with single frequencies, but they have many different frequencies and overtones. As the star evolves and gets bigger, so from the bottom to the top of this plot, you can see that the pulsation frequencies get lower, or the periods of the oscillations become longer. In the analogy of the music instrument, you can consider this as the stellar sound becoming deeper. The second feature you can see is that as you go up in this plot to larger stars, you can see that the amplitude of the oscillations increases. And again, in analogy to a music instrument, you can consider this as the stellar sound becoming louder. Now, Kepler allowed us to investigate this relationship between the pulsation frequencies and the amplitudes, again, over a much wider range of evolutionary states in red giants than was possible before. As you can see from this graph, every red giant that we detected oscillations in has its unique sound, its unique amplitude and frequencies. And we can therefore say that Kepler is basically listening to thousands of musicians in the sky, or in other words, us astroseismologists, Kepler allows us to listen to the greatest concert of red giant oscillations that we've ever witnessed. Now, to demonstrate this a little bit, we're going to be playing a sound file. If you can start playing that now, please. In this sound file, you will hear a sample of oscillations that are based on actual frequencies that we have measured with Kepler. These were scaled to the audible range of the human ear. As Travis mentioned, you could not hear the actual frequencies. And you will hear starting the sound of the smallest star, so basically the white line in the graph, which has the highest frequencies but the lowest amplitude. And gradually you will hear 3 other stars, lower frequencies but higher amplitude, entering the red giant concert. Okay, so you have just heard a sample of the acoustic oscillations based on actual frequencies of red giant stars that we have observed with the Kepler satellite, a Kepler red giant concert, so to say. With this, I will pass on to Thomas Kallinger, who will tell you in more detail about what we can learn from the oscillations in these stars.
Thank you, Dan. We have now heard an example for the amazing red giant concert that Kepler is listening. But what are these stars? They are a product of stellar evolution and represent the future of our sun. Stellar evolution theory tells us that stars like our sun spend most of their lifetime in a very stable configuration, slowly burning hydrogen into helium in their cores. But after the hydrogen tank is empty, they undergo dramatic changes. Can I have the next slide? This is illustrated in my first slide, starting with our sun in the lower left corner, where stars basically consists of a hydrogen burning core, an extended radiative envelope topped by a thin convective layer. After core hydrogen depletion, the remaining helium core collapses under its own gravity, causing the rest of the star to expand, and the stars cool down on the surface and become significantly bigger. In the so-called subgiant phase, which is indicated by the next sketch, they gain their energy from the layers surrounding the core, which started to fuse hydrogen into helium. This goes until the stars have become about 100 times bigger than our sun. Eventually, the shrinking helium core is so hot that it starts to fuse helium in an explosion-like event, causing a rapid contraction of the entire star back to about 10 solar radii. And the stars settle on the so-called helium core Burning Man sequence, where they will spend almost the entire lifetime of their remaining life. We know this general picture of these late stages of stellar evolution quite well from theory, but to actually confirm it with independent observations is quite difficult. This has now been done with Kepler observations, where we directly see these late stages of stellar evolution more complete and in greater detail than ever before. Can I have the next slide? By using the high precision photometric observations of Kepler, we could determine the oscillation frequency to an unprecedented accuracy, allowing us to determine most accurate stellar properties, like the mass and the radius of the stars, for a very large sample. Also, there might be more accurate measurements for individual stars from other instruments. It is the first time that we have them available for such a large sample of stars. On this slide, we can see how the red giant's masses and radii are distributed in the sample, clearly showing some detailed structure. It appears that many stars fall along a line-like structure that corresponds to the helium core Burning Man sequence. This does not only confirm the principles of stellar evolution, but will allow us to study the detailed properties of these late stages of stellar evolution that our sun will reach in some billion years. And now let me pass over to Katrin, who will tell us about the interesting RLeros star.
Thank you, Thomas. So can I have the first slide, please? A class of quite exotic stars studied with Kepler are the so-called RLeros stars. These stars have periods of typically half a day, and over just a few hours, due to their pulsation, their brightness can fluctuate by a factor of 2. Now, with their easily recognizable pulsation pattern, these stars are used as cosmic lighthouses to measure distances in the universe. The Kepler observations of the prototype and the brightest star of this class, called Lowry, and of over 40 of its class members, represent the most extensive and accurate set of measurements of those stars ever made. Next slide, please. Now, on these figures, you see Kepler data of 2 Lowry stars. What is being plotted is a measure of brightness as a function of time. Lowry stars pulsate regularly, many of them pulsate regularly with exactly repeating cycles, such as the star on the left. But a large fraction of the Lowry stars, including the prototype Lowry, undergo periodic changes in their light curve shape over a longer period of typically tens to hundreds of days. This behavior is known as the Blaschko effect. It was discovered over a century ago, and it has puzzled astronomers ever since. In our Kepler collection of over 40 Lowry stars, this modulation is observed in at least 50% of the stars. The Blaschko effect may be a rule rather than an exception. We do not fully understand the inner workings of these cosmic lighthouses. Now, with the accurate and uninterrupted Kepler data, we can look at the light variations over this longer Blaschko cycle in detail, and this is illustrated with the zoom on the right-hand panel of the Kepler data of the prototype Lowry. As you can see in the figure, we observe alternatingly higher and lower maxima. In other words, a variation in the pulsation with twice the actual period. This is the first measurement of a new pulsation feature, the so-called period doubling. The detection of period doubling is a major breakthrough because we think it's connected to the origin of the mysterious Blaschko effect. Only modulated stars in our sample, a few of them, turn out to show period doubling, and it only happens in specific Blaschko phases, so phases of this longer cycle. Hence, it brings clues for understanding the mysterious Blaschko effect. Now, next slide, please. Thank you. Why did the breakthrough come with Kepler? Here you see a comparison of ground-based and Kepler data. On top, the data resulting from a multi-site campaign, making use of 6 different observatories worldwide, and below our Kepler data of the star. It is striking that only a few months of uninterrupted Kepler data of the star Lowry uncover phenomena that were never detected before, not even with a century of high-quality ground-based data gathered with much effort and meticulously investigated by numerous bright astronomers. Now, this is not only because of the unprecedented precision of Kepler, but mostly because the satellite looks at the stars without blinking. From Earth, we are always confronted with things such as daylight, weather, and because these stars have periods of about 12 hours, it is very hard to catch consecutive cycles. It's not possible from one single site. And as you can see from the panel on the top, the period doubling could easily have been missed with data with so many gaps. And then additionally, we were just plain lucky that for our Lowry, that happens to lie in the Kepler field, that has been studied for over 100 years, and that was initially thought to be too bright for Kepler, the period doubling is so striking. So the prototype of the class gives us clues for understanding the whole class, as it should. Next slide, please. Now here you see an animation that shows the variations of RLeros light curve shape over the Blaschko cycle. The extremely accurate Kepler data have caused a dramatic overhaul in our understanding of the RLeros stars. And this is leading now to a much improved modeling of the pulsations of this type of stars for their use as cosmic lighthouses, and it also increases our understanding of other stars that show such large light variations. And with this, I pass on the word to Nathalie. Thank you.
Thank you. Thank you so much, Katrien. There we go. Is that good? Thanks, Katrien. Now what we'd like to do is move to the question and answer period. Most of our media are joining us on the phone, and so if you do have a question, you can indicate that to the operator by pressing *1 on your telephone. What I'd like to do is just remind you when you're asking a question, if you can state your name and affiliation, and where possible, if you can indicate which of our panel members you'd like to address your question. That will help to eliminate some confusion and help us to answer it more efficiently. So with that, I will pass it over to our operator.
Thank you. As a reminder, if you have a question, please press *1 on your phone. We now have a question from Robert Zimmerman, freelance.
Yes, this is Bob Zimmerman, freelance. I'm also a website is behindtheblack.com. Can someone give some details about what the theories are of why our RLeros stars are pulsating, a little bit background behind those stars themselves, and how this information is affecting those models or theories?
That's a question for me, I'm sure. So why are these stars pulsating? The pulsations in our RLeros stars are caused by a mechanism that we know as the kappa mechanism, and it's a sort of a valve phenomenon. It's caused by layers of the star where elements are partially ionized, and these elements get excited by the radiation coming from the inside of the star. As these layers move outside, the layers cool down, and the elements recombine, which again lets the radiation pass through, and the layers fall back. So that is the mechanism that is behind pulsations of many stars that you see in the sky. Not all of them, for example, not the sun, but for our RLeros stars it is. But I think your question also wants to address the models for the Blaschko effect. Is that right?
Yes, please.
Yeah. So the Blaschko effect is still a mystery. We have known it for over 100 years, and there have been some models that are more popular, that have become more popular over the decades. And I will tell you about the three most important ones. The first one, it's a set of models, are the resonance models. These assume that our RLeros stars, which are stars that are radially pulsating, actually also have some maybe smaller non-radial oscillations. So the stellar layers are deformed in a non-spherically symmetric way. And there might be a resonance between these non-radial modes and the radial modes that causes this modulation. That is one type of models. Then the second type of models are the magnetic models. These assume that our RLeros stars have a magnetic field that again causes this radial structure and this radial pulsation of the stars to be deformed. So the pulsations, because of the magnetic field and the Lorentz force that is attached to this magnetic field, causes the star to pulsate also non-radially. And then as these stars rotate over a longer time scale, you would get a different view on the pulsation of the star, and this would cause the modulation. And then finally, there are models that are recently gaining popularity, which have to do with the convection in the star. And the convection in the star, the turbulent convection, might be changed over longer time scales. The reason why, it could also be an internal magnetic field that has a complex structure. And the modulation of the convection actually changes the strength of the pulsation over this longer cycle. Now, all of these models have their problems, so we hope that with the Kepler data, we have clues to improve models or to explore even new ways. Does that answer your question?
Thank you.
Our next question is from Nancy Atkinson from Universe Today.
Hi, thanks for doing this. For any of the panelists, of the information that you got from Kepler, what was most surprising to you?
This is Hans Kelson. I mean, the whole thing that we finally get data of such amazing quality, that we actually study stars in all phases, in all evolutionary stages, and of different mass, of different type. That's the amazing thing for me. We actually study the stars of all types, and this is what I think is the unique thing about Kepler, that instead of just pointing to one star, observe it for a long time and learn about that one, we now have access to stars of any kind. And having said that, this also tells you, of course, that there's so much we still need to learn about studying all these data. There are thousands and thousands of stars that we still need to study.
This is Travis. I'd like to also answer this question. In the decade leading up to the launch of Kepler, for stars like the Sun, the campaigns to observe these stars from the ground are exceedingly difficult. And so only perhaps a dozen or a couple of dozen at most stars had been characterized in the way that we characterize the stars using Kepler. In the first year of the Kepler mission, we moved from having a couple of dozen of stars like the Sun with maybe a couple of weeks at most of observation to having 1 month each for a couple of thousand stars. So it's an enormous expansion of our capability to study this type of star and the oscillations and what they tell us.
Once again, if you have a question, please press star and 1 on your phone. We now have a question from Larry O'Hanlon from Discovery News.
Hi. We've seen recently a lot of controversy about a particular star, Gliese 581G. I don't know if any of this could have any application to a case like this where there's controversy about an exoplanet. Can anyone comment on that?
So what you're asking is, are there observations or analyses like the astroseismic observations and analyses that could help in a case like this? I mean, Gliese 581 is a tough nut to crack. I mean, you've got us, what, 5, 6, I've lost count how many planets have been detected around that star. But the point is that the radial velocity signature is very complex. You've got a star that's being juked around by many planets, so you have to take a very long series of data to be able to tease out all of those tiny signatures, and they are tiny. The amplitudes of every one is very, very small. So Kepler types of observations, if you have a system like that where you've got planets that are transiting, that of course gives you a lot more information. That's not the case for Gliese 581, or at least we don't think so. So that makes it a little tougher. Let's see, is it bright enough for astroseismology? I think it might be, or maybe it's on the borderline. Again, it's difficult, but with continued monitoring of radial velocities of Gliese 581, eventually it'll work itself out. We will be able to tease out all of those individual signals.
Thank you.
Bob Zimmerman is back online with a question.
Yes, I'm curious to know the stellar data that you've outlined here is describing stars that are different than the Sun, either larger, older, variable. Can you give us any information about any of Kepler's data that describes Sun-like stars, G-type stars? Is there any information there that you can give us?
I don't know, Travis, will you answer, or I can do it? We actually...
Yeah, I could just say that the star that I described, KIC 1102-6764, is a G-type star. It's more evolved than the Sun, and probably 10 to 20% more massive. But in the broadest sense, this is still a solar-type star. And we've observed something like 1,500 such stars for a month at a time. And we haven't got all of that data yet, but we're slowly working our way through it.
So actually, when we selected the stars that we should observe with Kepler, or focus on with Kepler for seismology, we in fact chose a lot of stars that are in a way surrounding, if you like, the state of what the Sun is in. So we have stars that have a higher mass than the Sun, and stars with lower mass. We have stars that are hotter than the Sun, colder and older and younger also. It's more difficult to find stars that are younger, but we have them in the list, so we can actually find stars that are very similar to the Sun in the Kepler data. And we are analyzing those data, and well, what it all tells you is, at the moment, in line with what we have told you here, namely that we tied all these observations into the stellar evolution theories, and we basically confirm that we know the distant future of the Sun is indeed going to be as the models predict.
As a reminder, if you have a question, please press star and 1 on your phone. We have no further questions from the phone at this time. Thank you.
Okay, very good. Well, that concludes today's media webcast. I'd like to thank the panelists, of course, for their time, and our Danish colleagues, especially Aarhus University. We are very pleased to be here. And I can say for the Kepler Science team that the analyses, the science, the partnership, everything about this partnership has far exceeded our expectations, and we look forward to many important discoveries in the future and continued collaboration. So for more information about Kepler, please visit us on the web at www.nasa.gov/Kepler. And thank you for joining us, and enjoy the rest of your day.